as we've done previously, let's look at what formulae we get given. There's just the one, and this is a formula for the instantaneous gradient of a function. And the way it works, and it's important to understand how things work, is we've got a point over here at which we wish to find the gradient. We take another point a little bit further away, x plus h, and we work out its y value, which will be f of x plus h. If we use those 2 points to find the gradient, we are finding an average gradient, and that's a really important concept. 2 points gives us an average gradient, whereas a derivative gives us an instantaneous gradient. If, however, we moved this second point a bit closer, we would get a better approximation of the instantaneous gradient, because our straight line would be kind of positioned somewhere like that. And this red line would have a better approximation for this red dotted line than the blue line was. So what happens is that we let h get as close to 0 as possible in order to find the limiting position of this tangent. Right, let's have a look at an example. So the nice thing with differentiation by first principles, and it is a formal process, so we've got to focus on the notation, but we know the answer before we start. We know from our kind of rules of differentiation that the derivative of 3x squared minus 2x plus 5 is 6x minus 2. That's where we've got to end up. Right, so we get given, as I say, the formula, and we plug in for our specific function f of x plus h. So the function is 3x squared minus 2x plus 5, so it'll be 3 to x plus h all squared minus 2 to x plus h plus 5. From that we subtract f of x. These brackets are really important. Leave those out at your peril. Right? From here it's just simplification. Once we've simplified, however, every single term on the top must have an h in it, and that's because we're then going to factor out an h in order that we can divide the top and the bottom by h. If you choose to write this next step over here, it must have brackets, otherwise you'll lose a mark. Don't ever put in a line at the bottom here like this, because by doing that you're implying that h is 0. H cannot be 0. This thing is not defined when h is 0. So we need to be quite sure that we don't show a 0 where h is at any stage. The last piece is to just make sure that the word limit appears on every single line while there's an h, and that it doesn't appear on the last line when there is no h. And then finally, make sure that your equal signs are on the left-hand side of the limit and not in the middle here. It's just an incorrect notation. This question's probably worth 5 or 6 marks, and very often people get down to the right answer, but they only get about 3 because they've lost marks due to poor and sloppy notation. It is a piece of theory, so you need to get it exactly right. Just now, using some differentiation rules, I like to get the expression that I'm trying to differentiate into what I like to call flat form. No fractions, no brackets, no surd signs. So this first one we can split up because we've got multiple terms on the numerator, right? This becomes 2/3 x to the minus 5. I would describe that as flat. It hasn't got any sort of fractions. This coefficient is a fraction, but there are no other fractions. And at this point only am I going to differentiate it. Notice that by not writing anything here, I'm implying all the while that this is y. If I just put an equal sign here, I'm going to lose a mark for notation because this is no longer y. This is dy dx. Likewise, I would lose a mark if I put a dy dx here because I haven't differentiated it yet. The blue one, I differentiate firstly by I need to factorize the top, and once I've factorized the top, the x minus 2's cancel, and I've now got it into flat form, and I then differentiate it, and only at that point do I call it f dash of x. Then this is also a notation you need to be comfortable with. What this is saying is differentiate with respect to x the stuff inside the square brackets. So the first thing I'm going to do is I'm going to get it into kind of flat form, right? So this is just a number, x to the half plus root 2 times x plus root 2. Notice that these are numbers, the square root 2's. Notice the difference between the first and the second term. The first term, the x was inside the square root sign. The second term, the x was outside. Right, now it's ready to differentiate. Just be aware that your last term, the derivative of root 2, is not, we don't start bringing the power down and reducing it by 1. The derivative of root 2 is 0. So obviously we don't need to show that, right? But don't differentiate a root 2. So there's your answer. Notice that on this line, the dx has disappeared because we've done the differentiation. Now, it's really important that we understand what a first and a second derivative actually tell us. The first derivative tells us about the function. It gives us the gradient. If the first derivative is positive, then the function is increasing or going uphill. If it's negative, then the function is decreasing or going downhill. And if it is zero, then the function is stationary. It's just, for an instant, just going horizontal. The second derivative tells us about the behavior of the first derivative. So if the second derivative is positive, then the gradient is increasing. And the gradient is increasing on a piece of curve that looks like this. Notice it's negative, it's less negative, it's zero, it's getting now more and more steep. This is what we call a concave up piece of curve, or a cup. Very easy to sort of recognize. If the second derivative is negative, then the gradient is decreasing, and we have what we call a concave down curve. Notice that the gradient was, say, 5 here, then 3, then 1, then 0, then -1, and it's decreasing as we move along. If the second derivative works out to be positive, we have what we call a point of inflection. And a point of inflection is a point on the curve where the concavity changes. So, for example, this curve is concave down, and at that point it starts becoming concave up. All the while here the gradient was actually, it's concave up, and it then becomes concave down. All the way here the gradient was actually increasing, and at this point it starts to decrease. This one goes from being concave down, gradient decreasing, to concave up, gradient increasing. You can get a situation where you have what we call a horizontal point of inflection. If we consider the function x cubed, right, at 0, so f dash of x would be 3x squared, and f double dash of x would be 6x. Just having a look at this, we can see that in fact 3x squared will never be negative, because if you square a number, it's always positively multiplied by 3, it's still positive. So the function f of x equals x cubed actually never goes downhill, never has a negative gradient. However, it does have a gradient of 0 at 0. So it flattens off temporarily. It also has a second derivative of 0 at 0. And you'll notice that this piece of curve is concave down, and then this piece of curve is concave up. So this is a point of inflection, but it happens to be a stationary point as well. It's what we call a horizontal point of inflection. Right, now I want to show you a little model of all of this, which I hope will help your understanding. Right, so I've got a picture of a cubic function about to appear here. And what we will show is the y value, the gradient, and the second derivative at any point. So as I move along, you'll notice that at this particular point, the y value is positive, the graph is above the axis. The gradient is positive because the graph is increasing. And the second derivative is negative because the gradient's actually decreasing. And you can see the gradient's decreasing all the while I move along the curve. Let's just go to another point. Let's go to a point over here. Right, at this point over here, the y value is negative because we're below the axis. The gradient's negative because the graph's going downhill. But the second derivative is now positive because the gradient's actually started increasing. You can see as we're moving along now, the gradient increases, and it actually increases for the rest of this graph's life. We can show the point of inflection, and that's where the sort of the concavity changes. If you just watch this figure, well, in fact, these bottom two figures, you'll see that the gradient's actually decreasing as we move along. The second derivative is negative. At this point, the second derivative goes to 0, right? Somewhere around there, it goes to 0. But what happens is the gradient starts increasing, right? What I could do is show the tangent, and notice that the tangent's got exactly the same gradient as the gradient of the curve at that point. And you'll see a funny sort of thing. It sort of kicks over at the point of inflection. Watch, it's decreasing, and it suddenly starts. So it kicks over and starts increasing. Okay, the last thing I'm going to do here is I'm just going to show the gradient plot. So as I move along, what the red dot coming down from the top is representing, it's representing the gradient of this blue curve at any given point. So I'm going to trace that point as I move along. So as I move along, notice that the gradient is positive. The red graph is above the axis, but it is decreasing. And that's because we're on a concave down piece of curve. Right? Notice that the gradient is getting closer and closer to 0, and it is 0 at the turning point. Now the gradient goes negative, which is why the red point has gone below the axis. Sorry, and it stays below the axis, right? At this point, the gradient's been decreasing its whole life so far, but at this point, the gradient starts to increase, and that's why the red graph is now turned and is now turning back uphill. At this point over here, the gradient will get to 0 again, right? And then thereafter, the gradient will be positive. Right, I could show as well the second derivative of this. Right, so the gradient of a cubic function is a parabola, a quadratic function, and the gradient of the quadratic function, or the second gradient of the original function, is a straight line. So notice if we just concentrate on the red function, it's got a negative gradient at the moment, which is why the green dot is plotting below the axis. It has a negative gradient the whole way until its turning point, which is over here, and that happens to be the point of inflection as well. And then from then on, it has a positive gradient. The red graph is a positive gradient, and the blue graph is concave up at that stage. Okay, so that's kind of how it looks. So we're missing a few gaps in our line there, but hopefully that was helpful in terms of your understanding. Okay, so if we were paying attention in that simulation, then this question now becomes quite straightforward to answer. We want the first derivative times the second derivative to be positive. Now, the way you get a positive product is to have a positive number multiplying by a positive number, or indeed a negative number multiplying by a negative number. So let's look at the first one first. Positive by positive, we would need a positive gradient, which means that the graph must be going uphill, but at the same time that the graph is concave up. Now this graph is only concave up from the point of inflection to the right, okay? So where does it start going uphill while it's also concave up? From bigger than x bigger than 0.33, right? Alternatively, we could have both of the negative. In other words, we could have the graph being concave down, which it only is up to this point here, but going downhill. First derivative negative, going downhill. And that happens clearly from -2 to 0.83. Sorry, -0.83, the point of inflection. This next one's a quotient, all right? And it doesn't matter that it's a quotient. The way we're going to get a negative quotient is to have a positive divided by a negative, or indeed a negative divided by a positive. Again, let's look at the first one first. Where is the function positive, in other words, above the axis, but the gradient negative, in other words, going downhill? Now that happens from -2 to -0.5. Above the axis, but going downhill. The other alternative is for it to be below the axis with a positive gradient, in other words, going uphill. Now that only happens on this tiny little piece from 0.33 to 1. Right, it's below the axis, got a negative x value, negative y value, negative function value, but a positive gradient. We're now going to look at some optimization examples, and this is a bit of reading here, but basically we are told that these two lengths have to be the same, and that this, what we're trying to maximize is we're trying to maximize the area of this deck subject to the amount of railing that we've got to do these four sides being 30 meters. Now with all of these optimization examples, what one wants to do is introduce a variable and then get all the other information in terms of that variable. So for example, if I decided to let that be x, then clearly this will also be x. Right, now what I don't want to do is put another different variable on there. What I do know is that altogether, I've got 30 meters of railing to use, and I've used 2x so far. So I've got 30 minus 2x for these other two sides, right? But in fact, they are going to be equal in length. So I can take my 30 minus 2x and I can divide it by 2. So in fact, I get 15 minus x. So each of these sides is 15 minus x. Right, now I want to work out the area of this deck. So what I'm going to do is I'm going to divide it into two rectangles and add those two areas together. So the area, the thing that I'm trying to maximize, is rectangle number 1 plus rectangle number 2. Rectangle number 1 has got a sort of base of x and a height that is 15 minus x minus this x. So it's 15 minus 2x. So it's x times 15 minus 2x. The other rectangle, number 2, x times 15 minus x. And when I simplify all of that, I get negative 3x squared plus 30x. Now, if I had to visualize that as a sort of a function, I've got area over here and, sorry, plus 30x. And so I've got something that looks like that. And I want to operate over here. I want to know what x value gives me a gradient of 0. All right. So what I'm going to do is I'm going to differentiate this. dA dx is negative 6x plus 30. I'm going to make that equal to 0, and I get x equals 5. So the biggest possible deck area will be when x equals 5. What I've done here is I've done a little simulation of this, and I'll just show you that that is in fact the case. So notice that the area at the moment is 63 meters squared when x is 3. If I make x even smaller, the area gets even smaller. If I make x a bit bigger, you'll notice the area is growing happily, right? And it grows up to an area of 75 when x is 5. After that, it starts to shrink again. Right, let's look at another optimization example. This one over here, we're trying to make the area of this triangle as big as possible, subject to it having one corner on the origin, it having a right angle here, and it's having its third vertex on this function f of x equals negative x squared plus 8. So I need to introduce a variable. So what I'm going to do is I'm going to say, let's let the sort of x value of this point be x. So in other words, that distance along there is x. I now need the height of this rectangle. Now don't put in y, because every single point on this graph has the relationship that its y value is just the negative of its x value squared plus 8. So there is actually the height of this particular triangle, because it must have this point must lie on this curve. Right, now we set up an expression for the thing that we're trying to maximize, which is a, and so it's going to be a half the base times by the height. Right, and that becomes negative half x cubed plus 4x. What I'm going to do now is I'm going to differentiate it, dA dx. And in fact, I get negative 3 over 2 x squared plus 4, and I make that equal to 0. When I solve, I get two possible values. They're plus or minus 1,63, but in the context of this example, 1.63 is the x value that gives me the best possible area for my rectangle, for my triangle rather. And let's have a look at a little model of that. Right, so here's my triangle, and you can see that as I increase the x value, the area is getting bigger and bigger up to a point here, after which it starts getting smaller again. This little red dot that you may have noticed is actually the size of the area. So you'll see that if I trace the dot as I move this point along, what actually happens is that the area maximizes when x is 1.63. After that, it starts getting smaller again. Okay, we're going to look at a third and last optimization example, just because there's quite an important concept involved here. And that is that if you've got a function and the square root of that function, then they will have their maximum and minimum values in the same place. There'll be different values, but they will occur in the same place. We're going to use that in the next example. So let's just take a look. What we've got here, we've got a point B that moves, that it's always on this parabola. And then we've got another point over here, and the question is, when is point B closest to point A, right? So again, we introduce a variable and we let B be the point X and then not y, but in fact negative x squared plus 2x plus 1, which it has to be if it lies on this graph, all right? And then we use our distance formula, because that's what we're trying to minimize. We're trying to make this red line as short as possible. We're trying to work out for which value of x this red line will be as short as possible. So I use my distance formula. It's just an x value minus the x value minus the x value, 6 minus x, and the y value minus the y value. I simplify it all, but notice I end up with this as the length. Now the problem is, unless you've done some AP maths, you won't know how to differentiate that. But if we just jump back to the previous slide, the square root of a function, the minimum value or the maximum value, would occur at the same value as the function itself. So in other words, I'm going to define a new variable now, which I'm going to call L, and that's going to be the square of the function. That gets rid of the square root issue, and I can now differentiate L with respect to x, and I get this. I equate it to 0, which is what I want to do to find out where the maximum or minimum occurs, and then I'll solve it using my Casio calculator. And lastly, once again, we've got a kind of a model of that. We get an answer of 2 for our sort of shortest possible distance. And let's just take a look at this. So what we've got, notice that the length gets shorter and shorter up to when I get to 2. And again, this point C that's hovering around, what it's plotting the actual length of this red line. So you can see that it actually traces a parabola. In fact, it's actually not a parabola, it's a cubic function, as we would have seen. But there it is. It's not symmetrical, not a parabola, but there it is, with the shortest possible length being about 4,47, experienced when x is 2. Okay, so moving on now, we're now going to talk about rates of change. Rates of change is a really important concept. Whenever we differentiate something, what we are finding is we're finding what we call a rate of change. Okay, and the most obvious one that we find routinely is the gradient of a function, right? So what we are finding when we find the gradient of a function, we're finding a rate of change. So here's a different example though. We've got water entering or leaving a jar maybe, and it's dripping in or leaving. But the question is, what was the average rate of change of volume in the first 3 hours? In other words, from 0 hours to 3 hours. Well, what happened is that the volume actually went from 1 liter to 4 liters in 3 hours. So the average rate of change would have been 3 liters divided by 3 hours, or 1 liter per hour. Right. And so the question is, did the volume increase or decrease over that time? Well, it increased, and the reason it increased is because we've got a positive rate of change. A positive rate of change always means an increase, in the same way that a positive gradient means the function is increasing. Right. Notice it actually increased and then decreased, but on aggregate, it actually increased from 1 liter to 3 liters. If we use our derivative, we are finding an instantaneous rate of change. So remember, 2 points for an average gradient, a derivative for an instantaneous gradient. So the derivative of this function is negative 2t plus 4. If we put 1 into the first derivative, that tells us that that exact instant, the volume is changing at 2 liters per hour. And it's increasing because it's a positive quantity. If we put 3 in, we get negative 2, and that negative 2 is negative 2 liters per hour. The volume is actually now decreasing, and that's indicated by the negative sign. Whenever we differentiate displacement with respect to time, we get velocity or speed. If we differentiate velocity or speed with respect to time, we get acceleration. Right, and just for the scientists among you, if we differentiate displacement with respect to time, remembering that u and a are constants, we get u plus at. Now you'll recognize that as a formula for volume. If now in turn we differentiate volume with respect, not volume, velocity. If we differentiate velocity with respect to time, we get a.